Hello and welcome to today's IWCS webinar. My name is Connie and I'll be the WebEx producer for today's event. Now I'm pleased to turn the webinar over to Ed Fenton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously during the presentation. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference session or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we welcome Wayne Kachmar, President of Technical Horsepower Consulting in Vermont, USA, who will be presenting his paper on evaluation of 200 micrometer versus 250 micrometer coated fibers for non-traditional cable designs. Wayne Kachmar is President of Technical Horsepower Consulting, LLC, which provides technical support related to design and processing of optical cable. He is a 40-year veteran of the optical cable industry. During that time, he has developed many unique cable designs for many specialized applications, including optical sensor cables embedded in the Antarctic ice pack, flight-critical aerospace cables, medical laser transport cables, and numerous military applications. During his career, he has participated in many standards bodies, including EIA, NJATA, NICA, and SMPTE, to help create cable and connector test methods. In 1988, he founded Northern Lights Cable, Inc., which was acquired by progressively larger cable and connectivity companies, most recently TE Connectivity. Mr. Kachmar retired from TE Connectivity as a fellow in electro-optic engineering, their highest technical role. Mr. Kachmar is the inventor on more than 50 patents in fiber optic product designs and technologies. He holds an AAS degree in electrical technology from State University of New York. Wayne, we welcome you to present at today's IWCS webinar series event.
Thank you. Thank you for the very nice introduction, and I thank all of you for attending this webinar. As you can see from the title of the webinar, we're talking about evaluating 200 micron coated versus 250 micron coated fibers, and primarily for the non-traditional cable designs. And I guess the question is going to be, why are we doing this? And those of you who know me that know that I am mostly a specialty and a non-standard cable designer. We do a lot of standard cable designs, and we really have a couple of standard cable families that the majority of cables are made from or designed from. And I am particularly, I will point out that I'm an empirical engineer, so I tend to do a lot of work other than simulation, but rather testing and qualifications. And what we have today are tests that are geared to these existing design families. So we talk a little bit about what they do, what they don't do. Then we'll talk a little bit about how we defined what we needed for additional tests. What was missing, or why did we want to do something different? We'll talk a little bit about testing and then present some of the test results to give you an idea of why we did these tests. And in that, it provides us with a series of recommendations about testing or about how to use these different fibers, the 200 versus the 250 coated, which are basically a new product. Traditional cable designs are depicted here, and they're used for many years, and they've benefited from improvements in both materials and design criteria. You see the gel loose tube, the tight buffer, dry loose tube. You could add to that ribbon cables. All of these are families of cables have been around for a long time. Made some assumptions. For example, that the 250 micron coating would continue to be the standard. And to a great extent, designing, if the as an example, ribbon cables have a 250 micron center-to-center coating spacing. And to a great extent, our systems have done very well because we have continued to improve with materials and designs on these families. A good example of these types of things from many years ago is the Ford Model T or the Volkswagen Beetle. They came along for many years and just kept improving the basic design. More recently, think about aircraft like the DC-9, now known as the MD-80, or the 737. You have many, many generations of these aircraft, and the newest ones are fantastically better than their original ones, even though they look very similar. That's true with our standard designs of cables as well. So our existing test methods have yielded very good results for these traditional cable designs. Now, next generation cable designs, what are we going for? Well, we want smaller. We want them lighter, closer. Everything is packed in there. Basically, the magic number is more fibers per conduit. How much can we stuff in there? Because our existing cable spaces are full of a number of old cables, that many of which are still used, including copper cables. You have Cat5 cables in there. They all take space. And we want to reduce the costs, that we remove extra materials and processes, and we provide more features with less. So it's a continuing growth process. Now, when we do these things, we use a variety of things that we call our cable designer's toolbox. And those standard tools are specifications, which are pretty common and pretty familiar to most users, the history of our experiences, and a lot of this comes from end user demands. The smaller, lighter, easier to install is from the end users. We also do a lot of testing, and that testing tells us what designs work, what designs have sensitivities or problems. I won't say failures because they're designed for a specific application, and if it fails the test, we'll know that. But other than that, we do very well. So a lot of these things I refer to as the basic designer's toolbox. And if you look at the toolbox on the right in this slide, that's my dad's toolbox, if you will. It was a basic set of tools that he used to do things. And it wasn't very elegant, but he could get things done with it. And any of you who have been to my lab will know that the toolbox on the left, there's stacks of those in my lab because I am a tool user and a tool collector of every tool that makes sense for what I do. So I have a lot of fun with finding the right tool for the job. And in this particular case, we're looking at what kind of tools we use, if you will, and what's in our original toolbox. Well, the present test methods we use to determine the effectiveness of a coating are what we're interested in. We're not talking about stranding. We're not talking about jackets. We're going to talk about coatings on a fiber. So the IEC coating there, the Telcordia GR20, and by reference it ropes in GR409, EIA, TIA, RS455, and particularly 41A is a crush test. But basically the 455 is a series of FOTPs, or fiber optic test procedures, that are a menu that we use to choose the design criteria that we're going to test to. And of course, when we're talking about optical fiber, we're almost always talking about the ITU 652, 657 series of standards for optical fiber that define dimensions and performance requirements for optical fibers. So all of these are designed around geometry, crush, shore hardness, and they're focused on orthodox cable design criteria. So if you're thinking loose tube, ribbon, tight buffer, these tests that are existing do very well for those. So the question is really, what do we want to add to that toolbox? What have we added even to a great extent? Well, we've started with a new change, which is bend-insensitive fibers. These fibers allow us a lot more leeway in being able to manage the fiber before we stress the glass to the point where it wants to fail. We've improved our water penetration control methods. Many of you who have been in the industry for many years will remember a variety of gels and, prior to gels, waxy substances used to block water in cables. Now we use a dry material. Basically, it's a high-tech version of disposable diapers. It's a super-absorbent polymer. Works quite well and does an excellent job of stopping water in its tracks. But it has its own set of issues that come with it. We've developed a lot of new strength members. We initially used aramid yarns and, to a great extent, glass-reinforced plastic rods or even steel central members in cables. We now have a number of other materials, some of which are even extrudable. So we've added these basic components to the toolbox. Again, we do multi-purpose layers. We're asking that a material do more than one thing. So, for example, a material might not only be a buffer, but it may also be an anti-fungus agent. It might be a strength member, but it might also contain a water-blocking agent. We have better acrylate coatings. Over the years, we've seen significant improvements in how we coat a fiber to make it more handleable, more easily accessible, more usable in the field, more usable at a skill level of an installer that's not as high, and we therefore can use it in places where an installer doesn't have the clean comfort of a lab to work in, but rather might be working in a bucket truck in a pole or down in a manhole. We've increased the ease of handling and stripping. We've developed methodologies in our toolbox to make cables that were easier to break open to get to the stripping. In some respects, we copied what was done for copper cables so that technicians in the field didn't have to change things. And lastly, we're now going to smaller diameter coatings. This is the newest tool in our toolbox. And in this particular case, what we're doing is we are adding a whole variety of new materials. The real question that tends to come up with this is, how do we evaluate these tools for a particular job? So we start to follow an old adage. This has been around for a long time. And you've probably heard this in numerous forms. When the only tool you have is a hammer, then every problem looks like a nail. So we try and fit a particular problem into a given test. The real question that I focus on is that we find that our test methods tend to lag behind our new product designs and material developments. So we're actually falling behind in testing. We're using a test that may not necessarily be reliable or a standard that works well with the parameter that we're now looking to test. And I think this becomes a very, very big problem as we go forward. So, having set the stage, I'd like to move now into the meat of this presentation, which is test methods for dealing with 200 versus 250 micron fiber. So the first question I have is, will the new coatings, this is how we came about creating these test methods, will the new coatings provide adequate mechanical protection against abrasive materials such as new types of strength members or crystallized coatings? And the crystallized coatings I'm referring to, for example, are the powdered coatings that are used for water-swellable protection, or for, in some cases, antifungal protection and so forth. And what we have to recognize is that we're seeing smaller and lighter cables, and 200 micron fiber is a natural for doing that, but it's a 48% reduction in our coating volume. So we now have a new problem for our non-traditional design. Do we really have the tools in our toolbox to evaluate this upgrade of a material and a process? When we make a smaller cable and we put it in direct contact with things like strength members, and the strength members have additives, and some of these additives are very hard in terms of the crystals when they're dry. So what we're really asking is how well will this 200-micron fiber hold up to what we now ask a 250-micron fiber to do? And we are more likely to have these fibers, whether it's 250 or 200 micron, in intimate contact with more and different cable components, various strength members, which may have these additives added to them. So the usual question that occurs with something like this is, what can go wrong, right? Well, a lot goes wrong sometimes. So that's why we sat down and said, what are these additives doing? And we started to look at the additives we had, and this was a short list that I started with. And in talking with people, I found that that list is only the tip of an iceberg. I tend to, being an old cable guy, I tend to look at things from the perspective of what we want to stop. We want to stop water. Initially, we wanted to stop fresh water. Now we're stopping saltwater penetration as well, which requires a slight difference. We also want no fungus or no mold to grow in the cables. We've learned this from experience. We also will put materials in there on our strength members or in our jackets or tapes or what have you for lubrication or processing ease. But that initial list sounds great. Now we're adding components for flame retardancy or for the ability to flame retard without creating, if you will, environmental issues. We're adding new materials to improve the fiber from not being sensitive to rodent predation. We're adding materials to all these components to do multiple jobs. So when we do all of that, if you just think about strength member types and the additives that go into them, it's a long list of unknowns. I'll give you a good example of a strange one, if you will. Think about a blown fiber tube that contains multiple fibers. And during the blowing installation process, you're shaking the tube and creating some aeolian vibration in there. Well, if you have a dry core and you have crystalline superabsorbent polymer in there with these fibers with a 200-micron coating, are you abrading the coating enough to damage the fibers? Think about it. It's not one of those things we would normally expect to happen. And who's going to look inside a tube once it's blown in place? But over time, will those coatings have deteriorated enough so that if we get any kind of moisture buildup in there, that the moisture will still get to the glass and may or may not cause problems if the fiber is disturbed by another fiber being blown in afterwards? It's one of those strange problems you would not normally think about, and those are the fun problems that we'd like to tackle and find a solution for. So in that vein, we came up with this concept of taking an existing test with EIA, TIA, FO, TP41A as a crush test, and it uses valuable design data because it crushes things. But what happens if you now have aramid yarn coated with superabsorbent polymer in a dry crystal form in contact with the fibers? And the problem was that we only had 10 centimeters of distance under that test. And with our super deluxe, and I'll use that nice term for it because I think the fiber guys have done a fantastic job of developing super low-loss single-mode optical fiber. Over 10 centimeters, you really can't see an increase in attenuation that would be substantial over an entire length of cable. So we needed a longer gauge length. So we came up with the idea of extending the platen from 10 centimeters out to 25, and instead of one pass, folding it back and putting 24 passes on that fixture. So now we have a 6-meter gauge length, a little easier to see some results. And we said we're not talking about a flat, smooth, shiny surface, but let's start looking at a coated surface, something that would simulate the size of the crystals in a water-swellable component. And again, we've seen a lot of variability in what we've seen. Sizes have varied tremendously from less than a micron all the way up to 50 micron in these crystals, and they're hard. So we have a concern there. So we wanted a longer gauge length and a surface that mimics the coated strength member's roughness. probably giving it a worst-case scenario than you would see in a actual cable design. But the idea of the test is to see what we can do to damage or mechanically abrade the fibers. So in doing so, we chose 3 sizes that we thought would be popular, 15, 25, and 50 microns to do the test. And with the 24 passes in there, we felt we had enough gauge length to actually see a result. Now, this is the actual schematic of the test setup. We used a kilometer of fiber ahead of that gauge length in order to eliminate any of the cladding effects that would have been occurred from the source. So we were trying to be fairly fair about this and not try and look at a worst-case scenario. I believe that if you took the 1 kilometer out there and did that directly, you would see a lot of cladding effects as well. And then the compression tester just basically used these 2 platens and an optical power meter to read the delta of attenuation prior to, during, and after compression. Now, these are the actual fixtures we developed for this. These are basically steel plates. They're roughly 13 centimeters thick in order to give enough rigidity, and they're actually much longer than 25 centimeters in order to have a 25 centimeter paper on there. One of the difficulties was finding a way to adhere the paper to the bars, which had been machined flat, so that they did not cause a problem at the edge of where the tape sat. We didn't want to have extra compression at those points, which create high loss points. And this particular one shows a 50 micron paper on there. Now, we loaded that with fibers, and in actuality, this is one of the most difficult portions of this whole thing, was loading that much fiber onto that bar and that platen and not having any of the fibers cross each other. We used a yellow fiber so we could see it, and it's even hard in this slide to see it, but it was the best picture I could get of that. And to make sure that the upper platen did not impinge on any of the tape that you saw there, only on the actual surface, so that we didn't crush edges of the fiber and add additional strain. So we were very concerned about that. But on a production basis, I would clearly build a fixture where I had the 24 slots on either side milled in so that I could lay this thing in much more easily than doing it by hand and physically chasing each one to make sure there was no crossover point. That was quite a interesting process to do. Now, that generates a fixture that looks like this. This is our instron tester. The 2 platens are up there being crushed with 445 newtons of load. We used, our parameters were 10 minutes of time. So we had 25 centimeters of area compressed times 24 passes, which works out to 17.8 newtons per centimeter. And the grits that we used were 15, 25, and 50 microns. So the end result is we had all of this information put together. We set this parameter up as our initial set of tests with the 3 different versions of this. This is what we measured. And here you see the post-compression results of one of the fibers under test. And we use single-mode optical fiber, primarily G657A1 or A2, as we were able to get it from our suppliers. And we used a legacy fiber, G652. Now, anyone who knows me knows that I never throw fiber away. So I actually had a spool of one of the major suppliers' fiber from about 10, 11 years ago, which had a previous coating system on it. And it was a G652 fiber, and I held on to that and used it as a reference fiber, if you will, as a control for the experiment. And what we looked at was we measured the optical power at 1550 before, during, and after compression. We also measured and looked at the examination of the compressed fiber coatings post-compression. And you can see on these fibers small indentations along the entire surfaces of the fibers. we were unable to identify the actual depth of the damage, but we wanted to make sure that we actually damaged the fiber in this compression. So this is a picture of the 25 micron particles. The 15 micron particles actually did not cause any damage to the coating. So beyond this stage of the process, we did not include them in the further testing. So that was one of the changes that we saw in this process. We didn't run a report on something that wasn't going to change. Now, with that, we have to have a method of saying, what does this buy us? What did we gain by doing this test? Well, after exposure to the abrasive cable materials, will the coating still provide protection to the optical fibers? And this is a question that we wanted to find out. How do we decide that? So, we said, if we activate the water-swellable compounds, will it enter any compressed part of the coating and or reduce the coating's performance? Our biggest concern here was, how do we do that? So we looked around and we said, there's actually a pretty good test that's out there right now. And to that end, we chose to use coating strip force, because it's pretty much been an accepted method to test the quality of your coatings. If you looked at coating strip force before we, if you will, beat up the fiber, and afterwards, you have a pretty good idea of whether or not the moisture and the mechanical damage did anything to the coating. So we use that as our preferred qualification for test method 2. And what we did in that is we took the post-compression fibers and strength members that were imbued with various water-swellable agents, put them in a Petri dish, activated it with fresh water, approximately 2-3 hours of time with the water, dumped out the excess water, and then allowed the powder to dry again. 24 hours after it was dry, we took it to the standard fiber coating test setup you see on the left, which was in the instrument. We used a standard tool and pulled 30 centimeters. And basically, the nominal values on this is FOTP 31, is between 1 and 9 newtons for a 30 centimeter section of material. So with that, we generated some results. Now, these are the 25 micron results. And again, we actually did a series of each of these. So rather than creating an eye chart for you, we take the data, and this is the average of 3 of each of those values. So the legacy fiber, you can see, was a little higher initially, but under compression, you can tell the difference in coatings between then and now in value, in attenuation, and post-attenuation, pre-strip force, and post-strip force. You'll see a real significant difference. Now, as we go down from fiber suppliers A, B, and C, you'll see that the values were pretty consistent. The 250 micron, slightly less than the and loss than the 200 micron, but not a significant difference. And post-attenuation, they all pretty much return to their pre-attenuation, post-compression. The attenuation stayed pretty much where they want to be. The interesting part, and this is where we were quite satisfied that our choice of the strip force test, it showed a pretty consistent drop of coatings on the 200, 250. Slightly more on 200, but not a significant, not statistically a large difference. And because we only did 3 of each, it wasn't a large enough population for us to get a standard deviation. But these are the averages of those 3. And not significant differences between the 3 samples. There we go. This is at 50 micron, and here you'll see that we didn't even include the legacy fiber because at the 50 micron compression, the fiber didn't survive. Clearly an indication that our coating systems have improved significantly between 10 years ago and now. And again, the results between the two were a little more aggressive, but not significantly. Next slide, please. So what the data showed us, that our coatings are sensitive to abrasive surfaces above 15 microns, at 25 and most likely at 50. So what that tells me is that legacy coating systems would not be viable, which we sort of expected in this more aggressive environment, which means that we can design cables today we couldn't design 10 years ago. Moisture access to the coatings is reflected in the ultimate coating strip force, so that's a I believe, very viable test that we should continue to use, and it should become a much more popular tool in our toolbox. And the good news in this is the major manufacturers that we tested of the 200-micron coated fibers have really done their homework. Even though it's half the material, the performance is almost equal to the 250-micron fibers. So I give it to the fiber people who make this stuff, who make the glass and the coatings. They have really done a fantastic job. Next slide, please. And so where do we go from here? Well, it would be nice to do some temperature and humidity cycles, some, if you will, highly accelerated life testing or halt testing on these. I'd like to do so and actually vibrate the coated fiber samples while they're in contact with these abrasive plates. I haven't figured a way to do that legitimately at this point. And as other fibers decide to provide 200-micron coated fibers, I would love to have samples to test. So any of the fiber suppliers out there who feel they would like to get some of this test data, I would be happy to have you contact me and send me some samples. We can do some testing. Next slide, please. And basically, the conclusions we've come to are that these smaller coating systems on the fibers will work in these very aggressive abrasion environments, as well as the 250, but way better than the legacy fibers. But we do need to do further environmental conditioning to validate long-term use. I think that would be important to see how we could do a temperature, humidity, or even a salt spray test. Both the 200, 250 suffer in these environments, in these very abrasive environments. So we have to think twice about when we're manufacturing it, what kind of abuse do we do to this cable or to these fibers in the process, or even during installation? So those are questions that we should be asking now, and those questions are new ones to go in the toolbox. And every time we add a new material next to a coated fiber, we need to have some method to validate its ability, whether it affects coating integrity. And we propose these as example tests to do that. And then last slide, please. Well, thank you very much for your attention, and hopefully you have found this interesting or at least informative. Thank you.
And thank you, Wayne. At this time, we will take as many questions from the attendees as time permits. I'll start with this first question. Are gel loose tube, tight buffer, and dry loose tube fiber coating designs each used in both indoor and outdoor deployment applications?
All of these are used in different applications. Different manufacturers have come up with dry core tubes for both indoor and outdoor applications. They are quite successful in many of the different ones. Tight buffer has been used mainly in indoor applications or in tactical or applications outdoors where it is generally going to be handled or processed, or the cable itself is being used in a more mobile application. Although some manufacturers have developed tight buffered cables for outdoor use that have survived quite well over the years. So there are basically two fields for each of these, but you have to also recognize as we change designs, that becomes even more of a question that will change as time goes on, because we're no longer able to define just an indoor or an outdoor cable. And in many cases, we want a cable that goes from outdoor to indoor, so it's flame retardant, meets safety requirements, might be low smoke, zero halogen, but also able to survive 30 years out in sunlight.
Okay, thank you. Next question. Are the new strength members still aramid yarns or something else?
Well, we're seeing, other than aramid yarns, we're seeing mixtures of elongated some extrudable polymers, some liquid crystal combined materials that are pulled and, if you will, elongated enough to provide tensile strength. We're also seeing mixtures where, in order to get enough grip on a connector, we're mixing polyester or other polymers with aramid yarns. We're also seeing coated fiberglass strands being used. And if you go to the yarn manufacturers, you'll probably find a half a dozen new variations to be presented. I suspect that the coming IWCS virtual conference, you'll actually see some papers about that.
Okay, thank you. Next, do you see 200 micron fiber coatings becoming the norm versus the current 250 micron standard?
I suspect over time they're going to become much more prevalent only because of the fact that you're reducing the amount of material you're using. And as we are forcing ourselves down, I call it the semiconductor curve of cost, reducing the cost of that material will actually become a significant cost savings in order to continue to make fiber much more attractive as a transmission medium than copper. And of course, I'm sure the copper guys will argue with me about that, and that's okay, but that's a fun discussion to have.
Okay, thank you. Next, where is your control data on a fiber exposed to strength member and water without crushing?
That data exists from other sources in previous papers. I do believe that was part of in the initial paper, it was part of the listing of cited references and sources. That's been done mainly by the manufacturers of the fibers as part of their ITU 652, 657 qualifications.
Okay, thank you. Next, do you have plans to test 180 micron fibers? And again, there's another question here that says thoughts on even smaller reduced diameter fibers under 200.
I would love to have samples to test because I think at this point, once the fact that the 200 micron performed way better than we expected was a pleasant surprise. Again, as I said, I give the fiber manufacturers a lot of credit for being really able to have made major strides in improving both the fiber but the coating systems. And I'd love to see what a 180 micron would do in this environment. I'd also like to try a totally different test with a 180 micron fiber, and that would just be the idea of a winding test to wind it around a spiral mandrel, because that smaller size brings up a whole series of questions of whether it would actually deform or not, because once they get beyond a smaller size, the amount of glass predominates, and therefore the shore hardness of the coating is put under more stress. So that could be a very interesting set of tests, and maybe a whole other paper.
Mm-hmm. Next question is, what is the net impact on fiber-proof testing on 200 micron?
I really can say I don't have an answer to that. Fiber-proof testing is usually done in-line during manufacturing, and it's typically processed, I believe, in-line, and is using a three-axis measurement system. So it's outside of my realm of expertise, and I'm happy to admit that.
Okay, thank you. All right, next question. Can you elaborate what are the real abrasive environment that may damage the fiber, since the test was done on fiber but not jacket?
Okay, there's really three things that I would say have concerned me. One is I have taken some of the water-swellable tapes, particularly those that are used for salt water, and noticed that some of the particle sizes on the inside of the tapes that would be against a stranded bundle were quite large. The crystals were quite hard. And the size was typically somewhere between 15 and 20 microns that I had seen. And it varied from one manufacturer to another as well. But that was one of the biggest areas, is wrapping a core with a set of fibers with a tape. A second one is the actual strength members, where we're seeing very small cables where the strength members and the fibers are intertwined with one another. And this occasionally occurs in the microcable categories, where you have a single fiber or two fibers or four fibers in a very small package, and the fibers and the strength members are intertwined in order to provide tensile strength. They're all parallel. But now you have that material that's attached to the aramids or the fiberglass, and it's touching it. Now, if we add fiberglass, you have the concerns of fiberglass ends that break and are sharp, and they could also impinge on the fiber. The third area that I am concerned with is that we're starting to use jackets that have to actually have a way to grip the core, the yarns, and therefore when you put fiber and yarn and jacket together, because you're not looking at a smooth inner surface, but you're looking at some surface that will interact with the yarns, you may actually force that down against the fibers.
Okay. Thank you.
And recognize, too, I should say, that it's getting down to very, very tiny cables. We're looking to put more in less space all the time, and especially as we look at trying to fill the niches in these conduits, the smaller cable wins every time because there's less and less room.
Thank you. Next, what polymers are the strongest coatings you have tested? Are there unmet needs in the market for higher performing polymers?
There's always room for a better performing polymer in terms of extrudable strength members that are flexible, that can be flexible, are the ultimate goal, so that you're buying, if you will, an exact shape. And a lot of time the work was developed to allow these materials to be oriented in one direction. And the orientation of the polymer to give you a very, very high strength is definitely a market that I think is still open. And again, that's me speaking, a network or a company.
Okay, thank you. We've got time for one, maybe two more, Wayne. Next question is general thoughts on splicing differences between 242, 250, and 200 micron fibers. And what is the able to splice a 200 to 250 micron, assuming the same MFD?
Okay, I'm not sure that relates to this paper, and I'm not sure I can necessarily answer that. Your concern was splicing 250 to 200, or the question was 200 to 250 micron splicing, and I'm presuming this is fusion splicing you're talking about. So under that circumstance, I would say that's a question for the fusion splice manufacturers. But I do believe that on coatings, once you put a splice splint on it, the coatings become irrelevant in size.
Great. Okay, thank you. At this time, we'd like to thank you, Wayne, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Wayne after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, November 20th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 68 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next 69th annual international conference will now take place virtually in October of 2020. Please watch your inbox social media, and our website as this exciting information becomes available. Also, the next UL and IWCS China Cable and Connectivity Symposium will take place on Tuesday, March 23rd through Thursday, March 25th, 2021 at the Marriott Hotel City Center in Shanghai, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.